Now we're going to explore further finding the initial value. So the initial value is not necessarily always n equals to 1. Sometimes we need to determine it by the question. Now I alluded to this before in the previous question where I said that I always wanted you to remember step 1 as finding the initial value, proving that's true, not that n equals to 1 is true. And that's because a lot of students get familiar with n equals to 1 and think that it's always going to be n equals to 1, which is not the case. So let's have a look at a question where n does not equal to 1 for the first term. So in question 2, we want to prove that 1 plus 3 plus 5, so on, to 2n plus 1 equals to n plus 1 squared by mathematical induction. Now, remember the 2n plus 1 was just the general formula for each of the terms in this equation. So if you this represents the first, the second, and every single term in that, yeah? Okay, now what I want you to work out is what is the initial value of n to get the first term. And remember how we do that is firstly by considering the general equation and then the first term. So we want to work out what does n have to equal for it to equal to 1. And so we can just quickly work that out. 2n plus 1 equals to 1. 2n equals to 0. So therefore n must equal to 0 for the first term to equal to 1. So that's why in step 1 we want to say show it is true for n equals to 0. So what I want you to think about is your first part of step 1 is always finding out the initial value of n just by doing this. And then you can say show it is true for n equals to whatever value it is. Now I think it's always good to check, so substitute 0 in there, you know that equals to 1. Whereas, can you see if we actually just put in n equals to 1, we'd have 2 plus 1, which is 3. So then we'd actually be starting off with the second term, which throws this whole thing off because we're not having that initial starting point, that initial push for everything. Okay, so how do we show it's true for n equals to 0? Well, we would consider the left-hand side first. So we have, using this general formula, 2 times 0 plus 1, which equals to 1. And then we consider the right-hand side. So using this equation, we have 0 plus 1 squared, and that equals to 1 as well. So we can say that the left-hand side does in fact equal to the right-hand side. So therefore, it is true for n equals to 0. Okay, so now we've done step 1. Remember what step 2 was? Yep, so that was the assumption that we make. So step 2 was making the assumption that this is true for n equals to k. That is, when we substitute in k, we're making the assumption that the left-hand side does actually in fact equal to the right-hand side. So can you see how all I've done here is just put k into wherever there's n. Now, remember how step 2 is important because we're always going to be using that assumption for step 3. And if you don't use that assumption, you know something's wrong. Okay, moving on to step 3. Now we want to show that this is true for n equals to k plus 1. That is showing that this left-hand side equals to this side, okay? That's what we want to do in step 3. Show it's true for n equals to k plus 1 by showing that this side equals to this side. Now, how do we get this equation over here? Well, the left-hand side, what we do is we add an extra term, this term over here, because we're having k plus 1, so that plus 1 is that extra term. And so we just substitute k plus 1 into this equation here. So we have 2 multiplied by k plus 1 plus 1, so that becomes 2k plus 2, plus another 1 becomes 2k plus 3. So we've just worked out our extra term. Now, on the right-hand side, I've just substituted k plus 1 into n. So I have k plus 1 plus another 1, which gives me k plus 2 squared. Yeah? And this part over here is just the same as what we had originally. So it's the same as what we had in step 2. And that's important to remember because when we use the left-hand side, we need to use that assumption that we made in step 2. Can you see how here, this part, so the 1 plus 3 plus 5 till 2k plus 1 looks exactly the same as the left-hand side in step 2? So instead of writing that part, what I'm going to do is substitute k plus 1 squared into it. Yeah? So I'm substituting that for this section. So now it's going to become k plus 1 squared plus the remaining 2k plus 3. And somehow, you always want to keep in mind, what am I actually doing here? What I want to do is make this look like the right-hand side, right? So always keep that in mind. How am I going to do that? Well, there's nothing I can really factorize or do here. So I know I need to expand first. So expanding k plus 1 squared, that becomes k squared plus 2k plus 1, okay? And now I'm just going to simplify that. So the 2k plus 2k gives me 4k, 1 plus 3 gives me the 4. So now I have k squared plus 4k plus 4, which looks very similar to this, doesn't it? And now we know I just need to factorize that, make into a perfect square of k plus 2 squared. And you can see that looks exactly like the right-hand side. So that equals to the right-hand side. With this, you always have your eye on this, and you're just trying to make the left-hand side, we're manipulating this value to equal the right-hand side. So since the left-hand side equals to right-hand side, we can say, therefore, it is true for n equals to k plus 1. So we've proven this over here. And that means if we've proven it's true for n equals to 1, and now we've proven it's true for n equals to k plus 1, we make our concluding statement. Therefore, the statement is true for all integers of n is equal to 0 or greater than 0. Yeah? Now, can you see how I've written 0 here? And that's because in my first step, I worked out that n equals to 0 was my initial value. So be really careful to also write that in your concluding statement. Now, just for the purpose of space, we've written therefore the statement is, but the best thing to write is therefore this entire equation, what you have in the question, yeah, rewrite that, is true for all integers n is greater or equal to 0. And so you just copy the question into the concluding sentence, and always remember to check that you have the right n value here.